Somebody posts online, Ohm's law doesn't seem to work on my motor. And honestly, they're right. Plug in the voltage and the winding resistance, and you get a number that's wildly wrong. Measure the windings on a 5 horsepower motor, and you might read a couple of ohms. 480 volts over 2 ohms says 240 amps. The nameplate says 7.6. So what's actually limiting the current? It isn't resistance. It's something the motor generates itself. When the rotor spins inside the stator's magnetic field, it does what any conductor moving through a field does. It generates a voltage, and that voltage opposes the supply. It's called Back-EMF, counter electromotive force. So the voltage actually pushing current through those windings isn't 480. It's 480 minus the back EMF. And that difference is tiny when the motor is spinning freely, which is why a healthy motor running with no load draws surprisingly little current. Now think about the instant you close the contactor. The rotor is not moving yet. No rotation means no back EMF. 0. So the full 480 volts lands across nothing but winding resistance and reactance. For that instant, the motor genuinely is close to a dead short. That's your INRUSH. We call it locked rotor current, and it typically runs 6 to 8 times the full load amps. So our 7.6 amp motor pulls somewhere around 46 amps at the moment of start. It only lasts a fraction of a second. The rotor spins up, back EMF climbs, and current falls back to normal. And this is exactly why the thermal side of a breaker is slow on purpose. That was episode 27. So where does full load amps actually come from? Start with horsepower. 1 horsepower is 746 watts of mechanical output. Divide by efficiency to get the electrical watts going in, because no motor is perfect. Then convert watts to amps. For 3-phase, current equals watts, divided by root 3 times voltage times power factor. Chain those 3 steps together and you can predict a motor's current straight off its nameplate horsepower. Let's do it. 5 horsepower, 480 volt, 3-phase, 90% efficient, power factor 0.85. Output is 5 times 746, 3,730 watts. Input is that divided by 0.9, 4,144 watts. Current is 4,144 divided by root 3 times 480 times 0.85. That's 4144 over 707, about 5.9 amps. Now, the part that catches everybody, a motor's current is not a fixed property. It depends on how hard the load is working it. Load it down and the rotor slows slightly. Slower means less back EMF, which means more voltage across the windings, which means more current. Jam the shaft completely and you're back at locked rotor, drawing 6 times, normal, indefinitely, until something stops it. Which is why my motor is drawing way too many amps is almost always a mechanical problem, not an electrical one. Which brings us to the thing that looks illegal, but isn't. For that 5 horsepower motor, the code table says 7.6 amps. Your conductors get sized at 125% of that. 9 0.5 amps. So, 14 gauge wire. But the breaker is allowed up to 250%, 19 amps. So you round up to a 20 amp breaker. A 20 amp breaker on 14 gauge wire. Last episode, I told you never to do that. On a motor circuit, it's correct, because here the breaker is only there for short circuits. The overload relay is what protects against overload, and it's sized off the nameplate. So, back EMF is the hidden brake on current. No rotation, no back EMF. Huge inrush. More mechanical load, less back EMF. More amps. Next time, back to the board. Grab a pencil, and I'll see you there.